So another one of the benefits of the convolution property is to actually compute convolution between two discrete time signals, as we're required to do in this example. So what we're going to do here is, first of all, compute the Fourier transform of x, then compute the Fourier transform of h. And since y is a convolution of x and h, I know that the Fourier transform of y is just simply going to be the product of the Fourier transform of x and the Fourier transform of h. And once I compute this product, then if I take the inverse Fourier transform, that's going to give me the time domain signal that I'm looking for. So let's do this example. We're going to have to divide this up into two cases. So the first case being when alpha is not equal to beta. And we know from one of the previous examples that we did very in the beginning was that x of e raised to power j omega is going to be equal to 1 upon 1 minus beta e raised to power minus j omega. And of course, we're given the information that the absolute value of beta is less than 1, and that's why the series is going to converge, the Fourier transform is going to exist. Similarly, h of e raised to power j omega, the Fourier transform of h, is just simply 1 upon 1 minus alpha e raised to power minus j omega. And y of e raised to power j omega is just simply the product of the two. So this is 1 upon 1 minus alpha e raised to power minus j omega times 1 minus beta e raised to power minus j omega. And all we're required to do next is to compute the inverse Fourier transform of y. The way we do that is through a partial fraction expansion. So y of e raised to power j omega, we can say, is actually equal to some constant a upon 1 minus alpha e raised to power minus j omega plus some constant b upon 1 minus beta e raised to power minus j omega. And if we do this expansion and then we can use standard techniques to determine the constants a and b, I'm not going to do them here. It turns out that capital A turns out to be equal to alpha upon alpha minus beta, and capital B turns out to be equal to minus beta upon alpha minus beta, because of which y of n, I can say, is actually equal to capital A times alpha raised to power n u of n plus capital B times beta raised to power n u of n. If I just plug in what alpha, what capital A and capital B are, so this just turns out to be alpha raised to power n plus 1 upon alpha minus beta u of n minus beta raised to power n plus 1 divided by alpha minus beta u of n. And just simplifying this a little bit further, the y of n, which is the convolution of x and h, is just simply 1 upon alpha minus beta all multiplied by alpha raised to power n plus 1 minus beta raised to power n plus 1 times u of n. So that's your answer, and you can actually go ahead and verify that when if you do perform the discrete time convolution between x and h when alpha is not equal to beta, this is exactly the same result that you're going to get with discrete time convolution. Now let's try the other case, because when alpha equals beta is a corner case, because when alpha equals beta, you have 1 upon 0, and this is 0 as well. So I mean, you either apply L'Hopital's rule here, that's something you could do, but I would do it in a different fashion. So for the second case, when alpha equals beta, we do it here. So case B is when alpha equals beta, your y of e raised to power j omega, it just simply turns out to be equal to 1 upon 1 minus alpha e raised to power minus j omega whole squared. And this is an exercise that I actually assigned just before this module, a few modules before this, and it turns out that y of n, which is, and I'm just going to give you the answer directly, which is the inverse Fourier transform of this y of e by j omega, this particular Fourier transform. It turns out to be equal to n plus 1 times alpha raised to power n u of n plus 1. And I can simplify this a bit further in the sense that u of n plus 1 actually starts at n equals minus 1. And I see that the signal at n equals minus 1, when I plug in n equals minus 1 here, this goes to 0. So therefore, this signal actually does not really start at n equals minus 1, but rather at n equals 0. So therefore, I can actually conclude that this is actually equal to n times n plus 1 times alpha raised to power n times u of n. And of course, the reason here is that since y of 0, y of minus 1 turns out to be equal to 0 here. And there you go. So for an alpha equals beta, this is what your result is. When alpha is not equal to beta, this is what your convolution result is. And once again, go ahead and verify that this is indeed the result that you're going to get when you do discrete time convolution, as we've done in the earlier chapter.